So today we are talking about two things. First thing is called slope field. Second thing is called Euler's method. You guys have seen Euler's identity, that e to the pi I equals -1, or e to the I theta is cosine theta plus I sine theta. Same guy, different thing that he invented. Shh, gentlemen. That is today. On Friday is our last day of new material. We're going to talk about growth and decay and how we can use differential equations to solve some word problems. Monday coming up is the last day of the semester. I have no scheduled agenda. We'll talk for like a minute at the start of class generally about the final exam, and then you'll use the bulk of the period just studying however you see fit. And then the exam is 1 week from today at 1 o'clock in this room. Questions on the calendar? Okay, project number 9 is officially assigned. It is due at the start of that exam, so it is due 1 week from today, but it's not a math project, so you can do it anytime, and you might want to get it out of the way sooner rather than later over the next 7 days. Everybody has the ability to get 100 on that project. All you have to do is show me that you have thoughtfully considered the questions and your responses. So your grade isn't going to be based on like how much you liked or disliked the course. I want constructive criticism on the job that I do and on this particular course that Caitlin and I have put together. So it isn't about giving me answers that I like. It's just about being thoughtful and answering the questions. Okay? So everybody can get 100 on this, but every semester I have people that get a lot less than that because they write like yes, no, maybe, and then like it's clear they took like a minute to do the project and their grade reflects that. Also, quiz number 5 is the one that I am, I don't even want to say it's optional. I've taken it off of the table. I'm going to hand it out on Friday. There are a couple of people that are going to take it for a grade because I've spoken to them individually, but my intention is not to have quiz 5 count, but I'll give it to you just for practice on Friday. Any questions on any of this? Quiz does not get dropped. No series. Yes. Yes. Other questions? 20th is a week from today, Wednesday. Okay, so we're on the top of page 68. We'll start with the daily summary, and can we go to Zach? So remember, ODE is ordinary differential equation. We'll go to Seamus for 1. Kevin? Okay, so first this word, do we know what it means? Saltwater. Instantly. Perfect mixing. So here's the idea. You've got this big old tub, 100 gallons of salt water. It already has some salt in it. And then you got this pipe coming in, and it's going to pour some more salt water into the tank at a rate of 5 gallons per minute. There's a hole in the bottom of the tank. Water is going to come out at a rate of 5 gallons per minute. And as Alex points out, we're assuming that the instant the water enters the tank, the salt water comes in, it's instantly mixed perfectly throughout. That's right. So we're gonna come up with a formula to tell us how many pounds of salt are in this tank at any moment in time. So how about we give a name to that function? So we'll let Q of t equal the number of pounds of salt in the tank after t minutes. So this thing right here translates into our initial condition. Can somebody say that as an equation? Everyone buy that? 0 minutes in, there are 4 pounds of salt mixed into this tank. Salt, total salt in pounds. Okay, and so ultimately, like I said, we're hoping to find a formula for Q of T so that we could know how much salt is in the tank after 1 minute or 10 minutes or 1,000 minutes. Some formula with T in it, okay? Now, turns out a differential equation is the right way to think about this, guys. So I'm going to write dq dt, which just represents the rate at which the amount of salt in the tank is changing as time passes. Yeah? Q prime. And I'm going to write it in plain English, and then we'll translate the English into expressions. But would you guys buy that the rate at which the salt in the tank is changing is the rate at which the salt is coming in minus the rate at which the salt is leaving? Is that fair? The rate at which the salt is changing is the rate it comes in minus the rate it goes out. So for example, let's say in the next second, 10 pounds of salt come in, and in that same second, 2 pounds of salt go out. By how much did the amount of salt in the tank change? 8 pounds, it's the 10 that came in minus the 2 that came out. So that's what that's saying. Okay, so let's start filling in. The rate in, okay, so the rate that the salt is coming in, it's 2 pounds of salt per gallon at a rate of 5 gallons per minute. Thinking about units, let me copy my dq dt over here. What are the units for dq dt? Pounds per minute, and I'm going to write them right next to the letters, right? Rates for the derivative are just the dependent variable units over the independent variable units. Let's see, it says 2 pounds per gallon, 5 gallons per minute. So how many pounds per minute are coming in? It's 10. Divide. 2 pounds per gallon, 5 gallons per minute. But if we just write it out, we'll see it. We know that the salt is coming in at 2 pounds per gallon multiplied by 5 gallons per minute. Yep. Gallons go away, and we have our 10 pounds per minute coming in. Minus. Now we need the rate at which the salt is leaving the tank. It's coming in at a constant 10 pounds per minute. I'm going to write the units, and that should help me fill in the fractions. So it's a pounds per gallon, just like it was before. Pounds per gallon times some number of gallons per minute. So I've got 4 blanks that we have to fill in here. 5 gallons per minute is still the same on the way out, right? So this is still a 5 gallons per minute leaving. It's that first guy that's the tricky part. It's the number of pounds of salt per gallon. The thing that's tricky here is that it's changing, right? The number of pounds per gallon, the concentration of salt in the tank changes at every moment of time. Brendan? Okay. It's going to have a variable in it. Let's look at the entire tank. How many pounds of salt are in the entire tank? Q. It changes. It's Q of T. That's what we called the number of pounds of salt in the whole tank, divided by how many gallons of water in the whole tank? 100. So that right there, Q over 100, is the concentration of salt. It's changing, but that's the expression that represents concentration of salt in the tank at any moment. You can put Q of T. Typically, we omit the independent variable, but Q of T is fine. Okay, so then let's push this together and write our final differential equation. So it says dq dt equals, we decided the first part was 10 minus 5 over 100 reduces to 1/20th. And then I'll shove the Q there at the end. Buy that? Is that okay? That's the differential equation that governs this problem. Any questions on any of the pieces? Yeah. So you might not be super interested about the salt in this particular tank, but like we heard in the beginning, this same kind of setup would work for pollutants in a river. Like you've got a company that is petitioning the town, say, hey, we'd really like to put our plant right here on the Deerfield River. And then you've got scientists that need to sit down and do this kind of calculation to decide if the river can absorb the pollutants that are coming in, right? Like maybe the concentration in the river isn't allowed to go above a certain governmentally set amount. And so same kind of setup, same kind of problem. That's the rate. Ultimately, we wanted a formula for Q, which we're going to find. So let's come down here to number 2. So unfortunately, integrating it isn't the technique because the Q is the dependent variable. If it were a T on the right-hand side, then you could just integrate both sides. But this is one of those trickier differential equations. You want some formula Q, it's going to have T's in it, so that when you take the derivative of that formula, you get 10 minus 1/20th of the original formula. And that's what makes it difficult. But we had a technique from last class that we used to solve certain kinds of differential equations, and that technique was separating the variables. So let's try it here. So what I'm going to do is move that dt to the other side. Like so. And I'd really like the q's to be with the dq. How do I do that? Divide by what? Everything in the parentheses. We've got to move everything. You can't just single out the q. You got to move that whole thing in the parentheses. So we get dq over 10 minus 1/20th of q equals dt. What would you do to mess around with the q? So the difficulty with adding, adding seems like the natural choice, right? You just add the 1/20th. Then it's dq plus, but that's a problem. No, it does not work in an integral. So that's the issue. That's why multiplying and dividing is the only thing we did last class. If it's dq over q. Yeah. That can't work in an integral either. dq over is fine. dq over q is fine. How would you get that to be an over? Like, are you going to divide by q? No, that's good. So dividing by q is a perfectly good thing. Like that would give us a dq over q. It would cancel here, but you'd still have a 10 over q on the one side. So this is our only option, I think, for getting the q with the dq. All right. Okay, so now we can integrate both sides like that. And then let's see, I'll do the hard one. That's the right-hand side. T. All right, but the left-hand side is harder. I'm not going to put the details. We'll just jump to the answer. But this integral right here, anybody see the technique? One over. This is a u substitution. What do we let u equal? Whole bottom. That thing right there is your choice for u. Yes. So we're going to get a times -20 in our answer. So we're just going to put the answer. You can check the details later. So it's a -20. And then if it's a du over u, what's the integral? The natural log. So this is going to be ln of u, which is that whole thing. Can't separate addition and subtraction in the bottom. Okay, so that looks good to me. What am I missing? Plus c, right? Let me do integral. So we'll just put the plus c on the right-hand side. But again, this piece right here, there's lots of details that we omitted. As I said, you can check it later. Okay, now we are going to ultimately solve for Q, but before we do that, why don't we just find the value of C right now? You can find C anytime, so let's just find it here. So we know that we have this initial condition that Q of 0 is 4, so Q becomes 4, T becomes 0. All right, so let's do that. We got negative 20 ln 10 minus 1/20th of 4 equals 0 plus C. Can somebody with a calculator crunch that through? We'll just get nearest tenth. Okay, while we're waiting on that, I'll just recopy my formula, and we're just going to change the C to this number that we get. Anybody have it for us? Anybody? I'm going to guess something like negative 40. How much? Great. Well, negative 40 is not close. Come on, that's pretty good. Okay, so that goes as our C, so it becomes T minus 45.6. That's fine. And now it's just algebra. There's no calculus left in this problem. Algebra to solve for Q. What do we do first? Divide by the negative 20 before we do that. And then once we move the negative 20, E to both sides, right? And then just a little bit left to do. So let's see. So it's going to give us 10 minus the 20th of Q equals, we said we were going to take everybody and divide by negative 20 and then raise both sides, raise E to both sides. So I think we're there. And then 2 more steps to solve for Q. Subtract the 10, multiply negative 20. So our final answer, Q equals everything we had before. Subtract the 10 times by negative 20. So I'll put my final answer here. Q of T equals negative 20. I'm just going to distribute this negative 20 through e to the T minus 45.6 over negative 20, and then plus 200 at the end. Quantity of salt is a function of time. Or quantity of pollution in the river as a function of time, right? That's why we care about it. It's not about salt. No. Like there's, like you could solve more interesting problems with the same exact technique. Let's solve some interesting problems. Let's get rid of So here's the, let's make sure we understand the formula. So if I said 1 minute into this experiment, how much salt is in the tank, what would we do? Just Q of 1, right? Just plug 1 in for the T. If anybody feels like doing that, that would be lovely. How about the long-term behavior of the salt in the tank as time passes? Sending T to infinity. So if you make T really big, then what about this fraction? Really big, but negative really big, right? Because that divide by negative 20. So e to the negative like a million is pretty much 0. Then times it by that, 0, and then plus that. So then I think we can say that the limit as t goes to infinity of Q of T is 200 pounds. And I think that makes an awful lot of sense because actually Alex said that answer before we did any of this. He said, oh, ultimately the stuff in the tank is going to be like the stuff coming in, right? Like the initial 4 pounds gets essentially nullified, right? We just, eventually it's just going to be what's coming in, right? And what's coming in is coming in at, what was the concentration? 2 pounds per, right? 2 pounds per gallon times 100 gallons gives us the 200. So it jives. Rob.
So like the salt wouldn't be mixed, it would settle at the bottom of the tank.
La 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 la. Rob. It depends. See, like it could be that the river is capable of taking the pollutant away faster than it comes in. So in this case, the stuff that was coming out was, it's just like, coming out at the same rate, right? Okay, next page. And let's go to Kevin, number 3, please. Oh, wait, you went already, didn't you?
Now we draw something called the differential equation. This entails drawing little tangent lines of the appropriate slope as
Okay, so here's a table. We've got t values, we've got q values, and then we've got the differential equation that we had originally set up. So if we plug t equals 0 and q equals 100 into the right-hand side of this equation, so we get dq dt is equal to 10 minus a 20th of 100. So what is that? 5. So let's fill in the next row. Now we're plugging 50 for t and 100 for q. There's no t, so again, it's 5, right? But it could have been, I mean, like we were fortunate that there was no t, but it could very easily have had t's and q's, right? So normally there would be both letters there. So in this case, it's 5, and in this case, it's 5, and in this case, it's 5, right? So if q is 100, it doesn't matter what t is. The derivative is equal to 5. Let's plug in, I left the t's blank because we've discovered that they don't matter. So if we plug 150 in for q, so 2.5 is that one. If we plug 200 for q, that's a 0. 250 for q, negative 2.5. And then 300 for q, negative 5. So here's what we're going to do with all of that information. I've got my graph over here. I'm going to go to each point that I've got in my table. And at the particular point, I'm going to draw a tangent line with the slope that's given by the last column, and I'll explain why in just a second. But go to the point 0, 100, 0 for t, 100 for q. All right, so I think that's right there. It's kind of my origin there. And we're going to draw a little slope, a little tangent line whose slope is 5. So maybe something like that. So the slope of that guy is 5. And then we move to the point 50, 100. And we draw another tangent line with the same slope because it's also a 5 in that next row. So I think we've got all of these parallel little tangent lines here. That was on the 100. And then on the, and then when q is 150, what's the slope there? It's half. So less steep, still uphill, but less steep. So we'll call that a slope of 2.5. And then you can just draw that same slope to the right. At 200, what kind of tangent lines? Flat, horizontal, right? So just draw a few horizontal lines there. And now we're going to go to the 250, and those have a negative 2.5 slope. So that means these ones are now starting to come downhill. And then how about the last row? Negative 5, so downhill and pretty darn steep, right? Maybe something like that. So first, let's make sure we understand why we were drawing these slopes. dq dt is the slope of a tangent line, right? It's like our very first definition of slope of tangent line, or first definition of derivative, is that it's the slope of the tangent line. So at each of these points, we have slopes of tangent lines. And you can imagine let's see here. Let's just jump to number 4. It says, on the slope field, sketch a few different solutions of the original differential equations. So suppose that we pick this point right here, and I've got a little part of a tangent line there, and so I'm just going to follow that tangent line just a little bit, right, up and to the right a little bit. But if I move up and to the right a little bit, what do you think happens to the slope of like the next wave of tangent lines that we didn't draw? Maybe it's not quite as steep, right? Because they were really steep at the bottom and then getting less steep. So then maybe it's starting to kind of curve, right? It's not as steep there and not as steep there. And when I pass through that 150 mark, I'm supposed to be a slope of 2.5. And eventually, what do you kind of think is going to happen as it's going to asymptote towards that 100? And so I really like drawing this kind of stuff on, these are called slope fields or direction fields. Like it just feels like I'm just like in the flow of these tangent lines, and you just sort of pick up the flow someplace. It's just a bunch of rivers, and you just jump in the river somewhere, and then it takes you wherever it takes you. Suppose that we had decided instead to start at this point right here. Go ahead and draw your best guess for the curve that follows the flow up there. Going to be going up or down? Concave up or concave down? Concave up, and you can kind of see it, right? And this one's also going to get sucked into the 200. What if, by some miracle, you happen to start right there at 0, 200, and it's just straight across? And this is 3 different pictures of what might have happened with different initial conditions on our salty tank. If you start with not very much salt in the tank, with 100 pounds or 4 pounds, I think we started with, yeah? Then you will increase slower and slower and hone in on the 200 long term. But if you started with an extremely salty tank, 250 plus pounds of salt in this tank, what's going to happen? It's going to get less salty because the stuff coming in is not as salty as the stuff that was already there. And eventually hone in, but from the other side on the same 200. And if you happen to start with a tank that had exactly 200 pounds of salt in it to begin with, then the stuff coming in is equal to the stuff that's already in there. And so nothing changes, right? You just stay at 200 pounds of salt the whole time. All right, so number 5, last definition, and then the activities. Equilibrium solution is 200. If you pick Q equals 200, you are at equilibrium. Nothing changes. Your derivative is constantly 0. So Q equals, what's that? No, not every slope field has an equilibrium solution. Okay, fair warning. The first problems here with the slope fields that are drawn are going to be pretty easy. You're going to learn in the activity a pretty intense calculation method called Euler's method. So expect to spend some time and raise a flag, and I'll help, right? Okay, go for it.